Okay, Trig, we got section 9.7, the fundamental theorem of algebra. I want you to look at a few pictures on page 596 and just to kind of show you. Let's see if I can zoom in here a little bit. Okay, so on the first equation, you have f of x equals x squared minus 4x plus 3. You'll notice that it crosses the x-axis 2 times, once, twice. So its discriminant, if you found the b squared minus 4ac, that would be a positive number. It has two real x-intercepts, two real zeros, and that would be at the numbers 1 and 3. So its factors would be x minus 1 and x minus 3. Well, what if we had it shifted up 1 unit? If we do that, then it only touches the x-axis in one spot. It has a 0 for a discriminant, which should tell me that it's got one real 0. And it happens to be at the x-intercept 2. So it has factors of x minus 2 and x minus 2. Later on, we're going to talk about multiplicities. This is a situation that has one real 0 with a multiplicity of 2. Well, then there's this other situation, right? H of x. And when you shift it up one more unit, going up to 5 here, then the graph never touches the x-axis. It has a negative discriminant, if you did the b squared minus 4ac, which should tell me that there are two complex solutions. And they would be conjugates of each other, 2 minus I and 2 plus I. We've talked about conjugates in the last section. So our factors, because every factor in the universe is written x minus. I know that some of you might argue, well, if you have a 0 of negative 3, isn't it a factor of x plus 3? Well, that's true, but really it's x minus negative 3. That's how it becomes x plus 3. So every factor in the universe should be written x minus. These are no exception. So even though it's 2 minus I and 2 plus I, which I could have only found out from using the quadratic formula, it becomes x minus, and then I use parentheses around my 2 minus I, and x minus and parentheses around my 2 plus I. And those are the factors. But like I said, you're only going to find that from the quadratic formula. Back up. Oh, getting close. Closer. How many zeros or x-intercepts can a polynomial have? That's a good question. The fundamental theorem of algebra. Here, let me just read it to you. Okay, the fundamental theorem of algebra. If p of x is any polynomial of degree n greater than or equal to 1 with complex coefficients, then p of x equals 0 has at least one complex 0. Here, I'll even show it to you for the people at home that want to write all this stuff down. Because they aren't listening to me anyway. So they're not listening to me, so I'm going to point to this theorem, and hopefully they'll have it written in their notes, right? Because they see the pen pointing to it, even though I'm telling the rest of you, don't write it down. The fundamental theorem of algebra is extremely useful, but it doesn't seem that way when you look at it. So if p of x is any polynomial, which is what we're dealing with, polynomials, the degrees are always greater than or equal to 1, with complex coefficients, then p of x equals 0 has at least one complex 0. So there's at least one solution to the polynomial. And it's complex because it does not have to be real. Now that's a theorem which is proven. We are not going to prove it. I will say this. The corollary that comes after it is far more useful than that fundamental theorem of algebra. I am not going to ask you to memorize that, but the next part you will. The corollary to the fundamental theorem of algebra, I'll abbreviate it FTA, says that the degree of the polynomial is a maximum number of zeros. So the most zeros you could possibly have is the degree of the polynomial. It does not mean that you will have that many zeros, but it does mean that you could possibly have that many zeros. Okay, so let's look at an example here. We need to talk about multiplicities. All right. Now, I'll back this up just a little bit so you can see a little bit more of what I'm going to talk about with this chart and all that good stuff. Scoot it over. Now, what's the leading term of this? Y equals x times the quantity x minus 1 squared. Well, remember, the leading term is found by taking x times x, in other words, the firsts. But don't forget that this is also squared. So this is really like saying x times x squared. That would be x cubed for the leading term. Now, I remember teaching you guys about end behavior, and it had everything to do with that leading term. First of all, the right end behavior had everything to do with the positive or negative leading coefficient. Since that leading coefficient is a positive 1, I know that the right end behavior is up. Since I know we have an odd degree, right? Odd degree meant that the left end behavior was opposite of the right. If it was an even degree, then it would have been the same as the right. So what are my zeros? My zeros, when I look at this, are the actual number 0 itself and 1. 1 comes from this factor right here. So, the zeros. This one has a multiplicity. How often does it occur as a factor? Well, it looks like it only occurs one time, so that's the multiplicity. But this one over here occurs twice. Yes, the exponent tells me how many times. So we have 0 for an x-intercept, and we have 1 for an x-intercept. And I taught you last year that you should attach the end behavior to the outermost zeros. Well, if you do that with this graph, you have this and you have this. Well, that really kind of doesn't make a whole lot of sense, because if you go up through the x-axis, won't you have to come down through the x-axis, and won't you be heading the other direction? How could you be going back up? Unless, of course, you understand something about even multiplicities. Even multiplicities bounce off the axis. Odd multiplicities cut through the axis. Even multiplicities bounce, odd multiplicities cut through the axis. So, if we understand that, then we can realize that our graph is going to come up and then come back down, and it really is going to curve and bounce off of that. Now, as you can tell, I did a sketch. I didn't really get real picky. If you want to graph that on your calculator, we can graph it on our calculators and find out exactly what happens to that. So we can pull out the good old graphing calculator and type x times x quantity x minus 1 squared. Then we can go graph that. I'm going to go back to the standard window just to look and see what it looks like. Okay, interesting. We're going to have to actually zoom in to look at that picture. And when I zoom in, then I can hit the enter button and it'll zoom in just on that part. So you can start to see that it does come above the x-axis and then back down and bounce. Okay, I'm going to do it one more time. So I'm going to hit the enter button one more time to zoom in just one more time. And it might be too much, yes. So I'm going to affect my window by moving it to the right, x maximum of, let's say, 2. So I can see that it comes up, bounces, and then leaves. Okay. Okay. Find the zeros of this polynomial. Well, of course I don't know what the zeros of that polynomial are, but I do realize I've got one thing that I remember from my Algebra 2 days. Always look for a greatest common factor. Okay, so GCF is a big thing. If you can pull one of those out, that's going to help you out a lot. Then I can look at this, and I can continue to factor it. I don't even need to use the quadratic formula or graphing it on a calculator, because I know that this is x minus 3 times x minus 3, or x times x minus 3 squared. So we know this is going to cut through the axis because of the odd degree, and this one is going to bounce off the axis because of the even degree. Okay? So the zeros in this case, zeros were x equals 0 and 3. What about this? Graph this thing. Well, I'll go through the same process I did just a little bit ago. So let's see if we can figure this out. I've got zeros at 0, at 3, and at negative 2. So 0, zeros, and just for fun I'll put down their multiplicities. 0, 3, and negative 2. Multiplicity 1, multiplicity 2, multiplicity 3. So what's the degree of this polynomial? The degree of this polynomial is 6. Okay? Because of the next theorem that we really talk about, the number of complex zeros, which equals the degree if the multiplicities are counted. So the number of complex zeros, we use the word complex because they don't have to be real, they could be imaginary, equals the degree if the multiplicities are counted. I also know this is degree 6 because you can take firsts and multiply them together. That's x squared, and that's x cubed. X times x squared times x cubed gives me an leading term, LT, I'll abbreviate it, leading term of x to the 6th, which gives me an end behavior that goes, let's see here, I've got a positive leading coefficient, so that means the right end behavior is up. I've got an even degree, so that means that the left end behavior is the same. So I'm going to attach that to the graph. At 0, we cut through the axis, and at negative 2, we cut through the axis. So this is cut through the axis, but at 3, because we have an even multiplicity, we have a bouncer. Now, just to give you an idea, this idea of number of complex zeros equals the degree, if you were to look at something like this, y equals x times the quantity x plus 2 times the quantity x minus 5i times the quantity x plus 5i, this is actually a 4th degree polynomial, right? 1, 2, 3. Take all the firsts and multiply them together, so we get x to the 4th. So it is a 4th degree polynomial. But there are only 2 real solutions in this situation. So that's why we talk about if you count the number of complex zeros, because there are 2 solutions right here which are complex. We got 5i on the left and negative 5i on the right. Those are solutions, but they are not zeros. The graph will only, of this thing, will only touch the x-axis twice. Okay. Next, I have a theorem that says the graph of a polynomial can cross any horizontal line, y equals d, at most n times. I'll hold that there for a second so that you can copy it or pause it. But I want to explain what that means. It really helps me determine the lowest possible, lowest possible degree. So a question like this comes along. Example 2, what is the lowest possible degree of this graph? So I got this polynomial I'm looking at, and I want the lowest possible degree. Well, according to the theorem, you need to find a horizontal line which hits it the most number of times. And it's not always the x-axis. In this case, I can find a horizontal line which cuts through the graph. How many times does it cut through the graph? 1, 2, 3, 4, 5. The least possible degree is a 5th degree. I should say 5. Is 5. Period. A 5th degree polynomial is what we're dealing with, folks. That's the lowest possible degree. Now, how could it be higher? Well, the other solutions might be complex conjugates. They might be imaginary numbers. That's why it could be higher. And they come in conjugate pairs, right? That's what the theorem says. Complex solutions come in conjugate pairs. So if I said to you, like conjugate pairs, just to remind you, 2 plus 3i, 2 minus 3i, those are conjugates of each other. So take this last situation. If I said name let's do this. Name 2 other possible degrees for this picture, for this graph. Name 2 other possible degrees for this graph. Well, you know it has to be bigger than 5, because 5 is the smallest. And if the other solutions are complex, they have to come in pairs according to that theorem. I could have 7 or 9 or 11 or 13 or 15 or 17, blah, 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 because they only have to be increasing by 2 because the complex conjugates come in pairs. I know these notes have a lot of stuff in them. Section 9.7's got a lot. I got one more example that we need to look at. Then we'll be done. I need to factor this thing. Bad news is I don't have any kind of greatest common factors. And so the first thing I need to turn to is my graphing calculator. So go to the graph to find a real 0. We just need to find one. So let's see here, 2x to the third minus x squared plus 18x minus 9. Okay, so I've got that first one done. Let me find a good window for it. Zoom 6. Okay, obviously I don't have a good looking picture of this thing, but I do see that it crosses the x-axis one time. So I'm going to go ahead and calculate the 0 here. Now when I calculate this 0, left bound, -1 looks good. Okay, right bound, +2 looks good. I know it's somewhere in between those two, right? I hit the enter button. It is 0.5. 0.5. So I got that information. So 0.5 is a solution. All right, I'm just going to write it as a fraction just for fun. Now, what do I want to do? Synthetic division, right? 2, -1, 18, and -9. Because I want to break this down from a cubic to a quadratic. So when you carry this down, you got a 2, and you multiply, and you get 1, and you add, and you get 0. And then I multiply again, and I get 9. Oh, whoa. Can I not multiply? Or what? 1/2 times 0. And they let this guy teach children. Okay, 18 plus 0 is 18. Multiply again, we get 9 and get 0. Why am I happy? Because we got a remainder of 0. And a remainder of 0 means that 1/2 must be a factor, which agrees with the picture and all that good stuff. So we have 2x squared plus 18. I don't even have to do the quadratic formula. How nice is that? I could simply solve this, right? Subtracting that to the other side, I get 2x squared equals negative 18. How did I know that I didn't need to use the quadratic formula? Because there was no linear term. As soon as you see no linear term, you can go ahead and stop doing the quadratic formula. But x squared equals negative 9. So when I take the square root of both sides, I get plus and minus 3i. But if you wanted to do the quadratic formula, be my guest, we could do that. The opposite of 0 plus or minus the square root of 0 squared minus 4 times a times c all over 2 times a. So we would end up with plus or minus the square root of, let's see here, negative 8 times 18, negative 144, negative 144. Right, so that's plus or minus 12i over 4, which is plus or minus 3i. So either way you'd like to do it, whether you'd like to beat yourself up with the quadratic formula. However, the quadratic formula, I'll say, comes in handy a lot. This was just a situation where I didn't need to use it. So anyway, the whole goal of this was to factor it, remember? So don't forget to factor. So what are my factors? Well, we had 1/2. How do we write that for 1/2? Remember, it's 2x minus 1. Now, if you are not remembering that, remember you set the 1/2 equal to x, multiply both sides by 2, and then you want the 1 to come to the other side. Well, the only way it's going to come is if you subtract 1, right? And then you'll get that equal to 0. Yeah, the world will be right and happy. So that'll be 2x minus 1. All right, now what are the other factors? We had x minus 3i and x minus negative 3i, which becomes x plus 3i. So there we go. We have all our factors. But only one of them showed up on the graph, and that's the key thing. One showed up on the graph. I found it. I used synthetic division in order to break it down to a quadratic for which I could use a quadratic formula. Well, what if I had a 4th degree? What if I started with a 4th degree solution? Well, then I would need to find 2 real solutions from the picture, and then I would use synthetic division twice. And if we run into that situation, you're going to have to ask me about it because some of you will get stuck. And what I mean by that is you'd come up here and you'd put another little box, and then you would keep going if you had to. You would not start back from the beginning. Okay? See you in class.